By the late 2000s, the United States Navy had a problem it had been ignoring for years. Its primary weapon for killing enemy warships was the Harpoon missile, a system that entered service back in 1977. The Harpoon could reach roughly 70 nautical miles. Against the air defenses fielded by modern navies, that range meant your launch platform had to get dangerously close before it could even shoot. The situation had gotten worse through neglect. After the Cold War ended, the Navy retired its anti-ship variant of the Tomahawk cruise missile. Long-range sea control strike, the ability to find and sink enemy warships at distance, quietly atrophied as the service focused on land attack missions and power projection ashore. Then, the strategic environment shifted. China invested heavily in what planners call anti-access area denial capabilities. Reports around 2009 highlighted the DF-21D, a ballistic missile designed to threaten aircraft carriers at ranges well beyond anything the Navy could answer with a harpoon. American carrier groups risked being outranged in exactly the kind of fight the Pacific demanded. The Navy needed a new anti-ship missile, and it needed one oh so quickly. Quickly enough that the service took an unusual step and turned to DARPA, the Pentagon's advanced research agency, to build what was supposed to be an operational weapon. The result was the long-range anti-ship missile, or LRASM, a stealthy, autonomous cruise missile that has since been called the ultimate ship killer. And that label raises a few questions that are worth chasing up. Why did DARPA end up running a program that normally belonged to the Navy's own acquisition pipeline? Why did engineers bet on a subsonic stealth and onboard targeting system instead of raw speed? And how did LRASM go from a contract award to hitting ships in just a few years? The wake-up call and the DARPA pivot. During the 1990s, the US Navy turned its attention almost entirely toward land. The Gulf War and the interventions that followed rewarded precision strikes ashore. Carrier air wings bombed targets in Iraq, Serbia, and Afghanistan. The fleet's mission centered on projecting power inland, and funding followed that priority. Ship versus ship combat drifted to the margins. The Navy had not fought a serious surface engagement since 1988, when it clashed with Iranian forces in the Persian Gulf. Anti-ship missile development slowed, and institutional knowledge about maritime strike thinned out. The Harpoon stayed in the inventory, while potential adversaries invested in newer, longer-ranged weapons. Now, by the late 2000s, the consequences were becoming pretty difficult to ignore. Chinese anti-ship ballistic missiles and modern cruise missiles threatened to hold US surface combatants at risk far beyond Harpoon's reach. Pacific-focused wargames kept producing the same rather uncomfortable results. American ships struggled to close within striking distance without absorbing hits first. The Navy needed something new, and the normal acquisition process was too slow. Developing a pipeline could take a decade or more, and planners didn't believe they had that kind of time. So in March 2008, the Navy made the unusual choice to use DARPA. And DARPA's role here was deliberate. The agency existed to move fast, take technical risks, and skip past the bureaucratic layers that slowed conventional programs down. Handing DARPA the lead signaled that speed mattered more than following the usual procurement sequence. DARPA issued a broad solicitation and received 9 proposals from across the defense industry. Lockheed Martin secured a key award among them. The program was structured around rapid prototyping, with multiple concepts running in parallel so designers could test different approaches before committing. 2 distinct missile concepts emerged under the LRASM banner. LRASM-A was a stealthy, subsonic design built on the airframe lineage of an existing cruise missile. It prioritized low radar signature and autonomous onboard targeting to survive modern defenses. LRASM-B took the opposite approach, pursuing supersonic speed to outrun defensive reactions rather than hide from them. It was technically ambitious and carried higher risk. Running both concepts simultaneously was part of DARPA's strategy. Each represented a different bet about what mattered most in a future anti-ship fight: stealth and intelligence, or raw velocity. And, well, that answer came in January 2012. DARPA cancelled LRASM-B. The supersonic concept had just grown too expensive and too complex to deliver on the accelerated schedule. Its technical challenges threatened to drag out development by years, which, well, defeated the purpose of using DARPA in the first place. The cancellation consolidated the entire program around LRASM-A. From that point forward, every dollar an engineering hour went toward the subsonic stealthy variant. Their bet was locked in. The missile would survive by being hard to detect and smart enough to find the right target on its own, rather than by outrunning defenders. That decision shaped everything that followed. It determined the airframe, the sensor suite, the guidance philosophy, and ultimately how the weapon would be employed in combat. The next challenge was proving that the concept actually worked. What makes LRASM different? LRASM's airframe started with something that already existed. Lockheed Martin built it from the AGM-158B JASSM-ER, a stealthy, air-launched cruise missile originally designed for land attack. The JASSM-ER gave engineers a proven, low observable shape, a reliable propulsion system, and a body that could carry a substantial warhead over long distances. The job was adapting all of that for a fundamentally different mission: finding and killing a ship at sea. The modifications were extensive. Engineers added a new sensor suite, new guidance software, and new terminal homing capabilities. The warhead is a 1,000-pound WDU-42B penetrating blast fragmentation weapon, which is a hell of a mouthful, that is designed to punch through a ship's hull before detonating inside. A Williams F-107 turbofan provides propulsion at roughly Mach 0.8, keeping the missile subsonic throughout its flight. Subsonic speed was a deliberate choice here, and it reflected the core challenge the missile had to solve. The open ocean is a deceptive environment. Targets move. A ship that was at a given position 30 minutes ago could be miles away by the time a missile arrives. Enemy warships also operate in groups, surrounded by commercial traffic, and they actively jam radar frequencies and broadcast false signals to confuse incoming weapons. Any missile that depends on continuous updates from its launch platform is vulnerable to having that link cut. LRASM was designed to handle the final phase of an engagement with minimal outside help, and that capability rests on a couple of pillars. The first is low observability. LRASM inherited JASSM-ER's radar-evading shaping and materials, which reduce its signature against enemy sensors. The missile can also fly flexible profiles, cruising at higher altitude for fuel efficiency during the transit phase, then descending to extremely low altitude as it approaches the target area. Sea-skimming flight close to the water exploits radar limitations near the surface. The practical effect is that defending ships and their escorts detect the missile later, which compresses the time available to track it, lock onto it, and shoot it down. The second pillar is autonomous targeting. LRASM does not simply fly to a set of coordinates and explode. It navigates toward a general search area using inertial navigation and GPS, hardened with military M-code to resist jamming. If GPS degrades or drops out entirely, the inertial system continues guiding the missile on its own. As LRASM enters the target area, its onboard sensors take over. A passive radio frequency and electronic support measure receiver, built by BAE Systems, listens for electromagnetic emissions from ships, including their radar transmissions and communications. This sensor can detect and locate emitting vessels without broadcasting a signal of its own, which keeps the missile covert during its approach. An imaging infrared seeker is commonly cited as providing the final identification capability, giving the missile a visual spectrum picture of the target in the last moments before impact. These sensors feed data to onboard algorithms that perform classification and prioritization. If the missile encounters a group of ships, it can sort through them and select the highest value target based on preloaded criteria. It can also coordinate with other LRASMs in a salvo to avoid duplicating strikes on the same vessel, distributing weapons across multiple targets. The missile still requires cueing from external sources to reach the right part of the ocean. Satellites, aircraft, or other intelligence assets provide the initial targeting data that tells LRASM roughly where to look. The autonomy kicks in for the hardest part of the problem, arriving in a contested area full of jamming and decoys, sorting real warships from clutter and false contacts, picking the right one, and guiding itself to impact. This combination defines LRASM's operational value. Reduced radar detectability meant the missile could survive longer in defended airspace. Onboard targeting meant it could complete its mission even when communication links to the launching aircraft were severed. Together, they produced a weapon that placed far less of a burden on the kill chain, connecting sensor to shooter, exactly the kind of resilience planners wanted for a fight against a sophisticated naval adversary. Proving it works. Now, designing a missile that could think for itself was one thing, proving it could do so in flight was a bit of another. The test program moved quickly, and each step raised the stakes. In July 2012, sensor testing began. A test aircraft carried LRASM Sea capacity on captive carry flights, keeping the missile attached to the aircraft while its passive receivers and imaging systems scanned the ocean below. The goal was confirming that the sensors could detect and locate ships from realistic altitudes and distances. These flights validated the hardware before anyone risked a free flight launch. By March 2013, DARPA awarded Lockheed Martin a contract to begin integrated flight testing covering both air-launched and surface launch concepts. The program was accelerating on two tracks simultaneously. In June 2013, engineers conducted push-through ejection tests at a land-based Mark 41 vertical launch system, firing a test body out of the canister to prove the missile's dimensions and booster configuration were physically compatible with the Navy's standard shipboard launcher. And then came the flight that mattered most. On the 27th of August 2013, a B-1B bomber flying from Point Mugu Sea Range off the California coast released an LRASM over the Pacific. The missile followed its planned waypoints during the transit phase, then switched to autonomous guidance as it entered the target area. Multiple vessels were present in the search zone. LRASM's onboard sensor detected the group, classified each contact, and selected the correct target, a 260-foot decommissioned ship operating unmanned. The missile struck the target. That single test demonstrated the full sequence the program had been built around. The weapon navigated to a general area, found its own target among alternatives, and hit the right one with no human guidance in the final phase. Momentum held through the fall. In November 2013, a second air launch test scored another direct hit on a moving maritime target, confirming the result was repeatable. Meanwhile, the surface launch track kept pace. In September 2013, a boosted test vehicle launched successfully from a land-based Mark 41 VLS installation. By January 2014, engineers had connected LRASM to the Tomahawk weapon control system aboard a test facility, showing the missile could integrate with existing ship launch electronics with minimal modifications. The third major air launch test came in February 2015. This flight added a new layer of difficulty. The missile flew at low altitude over water, then encountered a pre-planned obstacle along its route. LRASM executed an autonomous reroute, adjusting its flight path to avoid the hazard before resuming its approach and striking the target. Each test had layered a new demand on top of the last. First, prove the sensors work. Then prove the missile can fly, find, and hit a ship. Then prove it can adapt when something unexpected appears in its path. By early 2015, LRASM had passed every check the program asked of it, and it had done so on an aggressive timeline that matched DARPA's original promise of speed. The weapon was hunting correctly, at range, under conditions designed to stress exactly the autonomous capabilities that justified its existence. The fight behind the scenes. The test results gave the Pentagon what it needed to act. In February 2014, the Department of Defense authorized limited production of LRASM as an urgent operational capability. The designation meant that the weapon would bypass parts of the normal acquisition sequence and move toward fielding as a stopgap, filling the anti-ship gap, while a longer-term solution was developed. That decision carried a specific implication. Lockheed Martin would continue as the sole producer. There would be no open competition for the initial production run. Speed was the justification. The Navy had spent years watching its anti-ship capabilities erode, and officials argued that reopening the program to competitive bidding would cost exactly the time that they could not spare. Not everyone agreed, though. In March 2014, Raytheon and Kongsberg filed a formal protest with the Government Accountability Office. The two companies had partnered on the Naval Strike Missile, a proven Norwegian-designed system already in service with allied navies. They argued that the Pentagon was obligated to hold a competition and that their Joint Strike Missile variant could meet the requirements. Shutting out qualified competitors, they claimed, violated federal procurement law. The protest put the entire timeline at risk. A sustained GAO review could freeze contract activity for months. If the office ruled in favor of Raytheon and Kongsberg, the Pentagon might be forced to restructure the program around a competitive process. That restructuring would push first deliveries further into the future, potentially by years. For a weapon designated urgent, delay was the one outcome that the Navy had organized the entire DARPA effort to avoid. The GAO issued its decision in June 2014 and denied the protest. The ruling found that requiring new competition would introduce unacceptable schedule risk and duplicate work that was already completed. LRASM had flown, it had hit targets, and demonstrated its core autonomous capabilities. Starting over with a parallel evaluation would not serve the stated urgency. With the legal obstacles cleared, the program accelerated. DARPA awarded Lockheed Martin a contract worth approximately $200 million to speed the transition from prototype testing to early operational production. The money funded continued flight testing, manufacturing, preparation, and integration work needed to put the missile on operational aircraft. The stopgap label stuck, but reality was already diverging from the plan. Procurement timelines in the defense world rarely move as fast as threat assessments demand. Production rates ramped slowly. The follow-on program that LRASM was supposed to bridge toward remained years from delivering anything. Each budget cycle that passed without a replacement reaching maturity made LRASM less of a temporary fix and more of a permanent one. The missile the Navy had built in a hurry was settling in for a longer stay than anyone initially promised. From prototype to frontline. The Navy built LRASM to solve a Navy problem. The Air Force fielded it first, though. In December 2018, the United States Air Force declared early operational capability for LRASM on the B-1B Lancer. The bomber had served as the primary test platform throughout the flight program, and its weapons bay was already proven compatible. Air Force crews at Dyes and Ellsworth Air Force bases could now load the missile for operational missions. The B-1B's capacity made the pairing significant. A single aircraft can carry up to 24 LRASMs across its 3 internal weapons bays. One bomber sortie could put 24 stealthy anti-ship missiles into the air, each capable of autonomous targeting once it reached the search area. A flight of 2 or 3 B-1Bs represented a volume of anti-ship firepower the United States had not been able to generate from the air in decades. The Navy's own platform followed roughly a year later. In November 2019, the service declared early operational capability for the LRASM on the F/A-18E/F Super Hornet. Integration work had been underway for years before that milestone. Captive carry flights and flutter and structural load testing ran through 2015 and 2016, confirming the missile could be carried safely on the Super Hornet's external pylons at operational speeds and altitudes. Software integration and weapons release certification followed. A Super Hornet carries fewer LRASMs than B-1B. The fighter typically employs 2 missiles per sortie, but the platform operates from aircraft carriers, which means it can launch from whatever patch of ocean the carrier group occupies. A carrier air wing equipped with the LRASM-armed Super Hornets gave the fleet an organic anti-ship punch that did not depend on land-based bombers flying from distant airfields. Together, the 2 platforms changed what American forces could do at sea. For over a decade, the Navy's primary air-launched anti-ship option had been the aging Harpoon, limited to roughly 70 nautical miles and increasingly vulnerable to modern defenses. LRASM extended that reach to hundreds of miles. A carrier air wing or a bomber squadron could now engage enemy surface combatants from well beyond the range of most shipboard air defense systems. That reach fed directly into operational concepts the Navy had been developing. Distributed lethality, the idea of spreading offensive firepower across more platforms and wider geography, depended on having weapons that could strike at meaningful range. LRASM made the concept practical. A Super Hornet launching from a carrier hundreds of miles from the target, or a B-1B operating from Guam or Australia, could threaten enemy warships without closing to distances where their own platforms faced destruction. The shift also affected planning on the other side. An adversary defending against Harpoon-era threats needed to worry about relatively short approach corridors. Defending against LRASM meant accounting for stealthy missiles arriving from multiple directions at far greater distances, launched by platforms that might never even come within range of counterfire. One notable absence marked the initial fielding. A surface launch variant, fired from the Mark 41 vertical launch system that equips most Navy cruisers and destroyers, had been demonstrated repeatedly in testing between 2013 and 2016. Boosted ejection tests integrated with the Tomahawk weapon control system and compatibility trials had all succeeded, but the first operational increment focused exclusively on air-launched deployment. Surface launch capability remained a proven technology without a fielding date, held for a future increment that kept shifting to the right. The decision reflected both budget priorities and the logic of the urgent capability designation. Getting LRASM onto B-1Bs and Super Hornets addressed the most immediate gap with the fewest remaining integration risks. Surface combatants still carried harpoons and could rely on other weapons for self-defense. The standoff anti-ship role, striking enemy fleets at distance before they could threaten friendly forces, belonged to aircraft. So that's where LRASM went first. Early tests had proven LRASM could find and hit a ship on its own. The next question was whether multiple missiles could do it together. In December 2017, a B-1B launched 2 LRASMs during a single test event. Both missiles flew their profiles and struck their respective targets. It was the first demonstration of a coordinated pair, but the real combat would demand more. That larger proof came in April 2024. 2 F/A-18F Super Hornets each released 2 LRASMs, putting 4 missiles into the air simultaneously. All 4 navigated to the target area and met their test objectives. The significance was timing and coordination under conditions closer to actual employment. Previous tests had validated the weapon one shot at a time. This event showed multiple missiles launched from separate aircraft could operate in the same battle space without conflicting with each other. By then, LRASM had also crossed an international threshold. In February 2020, the US State Department approved the potential sale of up to 200 LRASMs to Australia. In July 2020, Australia announced plans to integrate the missile onto its own F/A-18F Super Hornets. The sale signaled that Washington considered LRASM mature enough to share with a close ally operating in the same Pacific theater that had driven the program's creation. Production had been climbing steadily. By early 2022, approximately 300 missiles were under contract with Lockheed Martin. Unit costs settled at around $3.2 million per round. Multi-year procurement agreements, locked-in production rates meant to build a significant stockpile. The original plan had called for LRASM to serve as a bridge. It was supposed to hold the line, while a more advanced follow-on weapon completed development. That follow-on kept slipping. Each year, the replacement failed to materialize. LRASM absorbed more of the load. A weapon labeled as a stopgap was becoming a permanent fixture. The Pentagon's response was to upgrade what it had. The AGM-158C3, commonly called LRASM ER or Extended Range, entered development testing with a target deployment date of around 2026. The C3 variant extends range significantly to an estimated 500 to 600 plus nautical miles and adds a two-way data link that allows operators to retarget the missile after launch. Survivability improvements are also included. The Navy is shifting new production toward the C3 this year. Meanwhile, the missile reached new platforms for the first time. In September 2024, an F-35C completed its first captive carry flight with an inert LRASM. In March 2024, an F-35B followed with its own carry test. Neither aircraft has fired the weapon yet, and integration work remains ahead. But the flights pointed toward a future where LRASM is available across the air carrier wing's primary strike fighters, expanding the number of platforms that can employ it. That expansion remained unresolved as of early 2025. The F-35 integration timeline had no public completion date. The surface launch variant still lacked an operational fielding decision, and the C3 upgrade had yet to finish its test program. LRASM was simultaneously growing into new roles and waiting on decisions that would determine how large those roles actually became. A ship killer that bought time. So LRASM restored a capability the US Navy had let decay for nearly 2 decades: the ability to find and kill enemy warships at long range. It got there by an unusual path. DARPA built what was supposed to be a stopgap on a timeline the normal acquisition system could never have matched. Stealth and autonomous targeting gave the missile a way to survive in defended airspace without depending on links that an adversary could cut. Fielding on the B-1B and then the Super Hornets put that capability into operational hands, and salvo testing with allied export commitments proved it could scale beyond single-shot demonstrations. The weapon's still growing. The extended-range C3 variant is in development testing. F-35 integration flights are underway, and the Pentagon is simultaneously pursuing Halo and other next-generation programs meant to eventually succeed it. Until those programs deliver, LRASM remains one of the few proven long-range anti-ship weapons the United States can put on target. The stopgap is holding the line. Thank you for watching.